Particle moves along a line such that acceleration in meters per second squared for t greater than or equal to 0 is given by this. Okay? That makes sense. You can even put in 0. Very nice. If the particle's velocity at t equals 0 is 5 meters per second, what is the velocity of the particle at t equals 3 seconds? Okay. So, we're relating velocity and acceleration. So, flashback slightly. In the physics, you're given that, actually it's acceleration with respect to t equals acceleration. So this is your general constant acceleration. Generally 9.81 meters per second squared and such. And this is equal to position vector with a second derivative. Probably like that. And so you take the integral of this and you get velocity with respect to time, which if you have a constant acceleration is something like this. And then you take the integral of that and get 1/2 at squared plus v naught t plus x naught. And these are your kinematic equations. Now this only works for a constant acceleration. Here we have some sort of Twilight Zone style acceleration, and so we're going to do the same idea, t plus 3 over t cubed plus 1 dt. We're going to take the integral of this from, what is the velocity of the particle? The particle's velocity is from 0 to 3. So we'll take the integral of this, and this will give us the rise in velocity from 0 to 3. And then we'll add on its initial velocity, which will be 5. So, man, I have no idea how to do this integral. So I look at it, I'm like, all right, maybe I can do a u substitution with this t cubed here, but then you're like, no, because you want a t squared. And you're like, well, maybe I can do separation of variables, but that's, no. There's a square root in there, so maybe it's a arc something. Nope, we're just going to do calculator. Yep. Calculator. I feel so bad using calculator. I know I probably shouldn't, but I shouldn't feel bad. Man, I'm not even sure I have enough parentheses to make this. So I'm going to use x instead of t, basically just out of convenience. So we'll do a square root x to the third plus 1. That's the square root. And we're going to do the window. We're going to go from 0, I'm going to say to 4. Yeah, maybe 5, 6. That way I don't have to scroll as far. And, so when we plug in 3, I don't know what the y value is going to be. So it's going to start off at 3 over something. Plug in 3, we get 6 over 27 plus 1, 28. Square root of 28 is 5. Maybe 2. I'll go from 0 to 5. Yep, we'll see what happens. Ooh. Surprisingly good guess. Aha! Interesting. Interesting. Okay, so now we're going to second calc. This integral. Lower limit. Lower limit is going to be 0. So slow. So tedious. And click, click. There we go. Enter. And now for the trip back. The voyage, if you will. And we're going to 3. 2.5. Oh, 3. Enter. Do the Riemann sum type whatnot. 6.71. Okay? 6.71. and that's our meters per second rise that we had. And then they said that our initial velocity was, so this guy right there, 5. So we'll do 11.71 plus 5 meters per second. Whoop. Highlight some of this. Move it over. Straighten it out. Move it down a little bit. Get rid of that crazy part up there. I feel proud of myself. Look right here. Right here. Whoop. So 11.71 right there. Yeah. And so I imagine this answer is right here just to trick you. Human performance trap. To see if you remember to add in that 5. So the answer for this one would be 11.710. This is how we did this one. So calculator problem, probably given about 3 minutes. You're given an acceleration. Acceleration is the second derivative of position. So we're asked to find the velocity, which is the first derivative. So to get from the second derivative to the first derivative, we're going to integrate. We do the integral. It's a crazy integral. So we graph it. We then use our calculator to find the area under the curve. The area under the curve is the integral, which told us the change in velocity, or speed if you will, from 0 to 3. And then we added in the constant, the c if you will, and that was 5. And that gave us 11.71. So as an analogy, a similar thing is done with the kinematic equations, except the kinematic equations have a constant acceleration, so they tend to be easier equations. And that is how we solve this problem. Go team. Excellent.